We got a good one today. This is really cool. This is really, really cool. All right, so again, what did we do last time? We basically went over the definition of DFAs, and we tried to prove these regular operations, union, intersection, and star. And we were able to show that through this Cartesian product construction that deterministic finite automata are closed under union. But then we tried to apply a similar argument to the concatenation operation. Wait, what did I say? For the three regular operations, did I say intersection? Union, concatenation, and star. And the thing that failed when we tried to do concatenation is that we basically have, some string and we have these two DFAs and we run in the first one and then we don't know when to jump over to the second one. So we didn't really have a good way of proving closure for DFAs, but we introduced this idea of non-determinism, which is basically, all right, we're going to introduce a new type of finite automaton, the NFA, non-deterministic finite automaton, which can take branches, which can split itself into different copies of the computation depending on which path it's in. And that was really cool because then it easily allowed us to, well, I guess the first thing is we introduced this idea. Then we wanted to answer the question, why are we doing this? Like, is it the same? Does it have the same power as a DFA? And we introduced this construction where we convert an NFA into a DFA by basically taking the sets of the NFA, taking the power set of that. So see here, well, this isn't the best example. Let's do, okay, so we're going to take this and convert it into this. So we have a 3-state NFA, and we convert it into a 2 to the power of 3 state DFA. And then this construction proves that they are in fact equivalent, so that any NFA has an equivalent DFA, and any DFA is just an NFA that doesn't happen to, that just has one state as its output of the transition function for every state alphabet character pair. So once we did that, then we're like, okay, so NFAs are the same as DFAs, but they end up being way easier to work with because we can easily prove closure of union. So this is union, closure of intersection, and then closure of star. And by the way, okay, yeah, so that's that. I was going to say something about intersection. Intersection is closed. They show it in 1.1. So then once we did that, and we're like, okay, so we have these ways of building up. And I guess one thing that I really didn't mention is that in introducing the finite automaton, we introduced this very important definition for this first chapter called the regular languages. And basically, a regular language is defined as basically a set of strings that is recognized by a finite automaton. So once we did that, we were like, okay, we can start building up these things, and then we come at it from a new angle. So once we show that these operations are closed under these regular operations, we come at it from a new angle, the regular expressions. And this is a syntax for describing languages. The regular operations we use to build up expressions, so syntax, that we call regular expressions. They're expressions that refer to languages. And this gives us a concise way to describe patterns of strings effectively. And from that, we basically, the goal is to show that we can convert regular expressions to finite automaton and vice versa. So basically showing another equivalence that we have, regular expressions, in fact, describe all the DFAs, all the NFAs, and they recognize the same set of languages. So they're equivalent in their power. And so this is the formal definition. We have like 3 base cases, and then we have the regular operations on regular expressions. Pretty easy. Examples. Let's see. So after we did that, so we did our proof. This is the important proof. A language is regular if and only if a regular expression describes it. So remember, our definition from 1.1 was that a language is regular if some finite automaton recognize it. So now we're extending that to basically show the equivalence of regular expressions and finite automata. So we're good there. So we do it in 2 directions because it's an if and only if. So the first direction is that if we have a regular expression, how do we make an NFA? Or, we can make an NFA because we just showed that an NFA is a DFA. So if we show it's an NFA, then we could just do our power set construction to make the DFA. So NFAs provide the scaffolding that makes it a lot easier to build on. DFAs are sort of too low level. And then the other direction, so this is a good example, and anybody that's reading through this book, I encourage you to take this string and then just construct this NFA from it, because it's pretty fun to do. Another example. So now here's the other direction of that if and only if proof, is that you have a regular language. So by definition, that regular language has a DFA. So because A is regular, it is accepted by a DFA. And then we show this procedure for taking a DFA and converting it to a regular expression. And the way we do that is by this extension of the NFAs into a generalized NFA, where basically transition arrows have regular expressions on them. And then we describe this recursive process where we continually rip out states until there's only 2 states. And when there's only these 2 states, then the arrow between the 2 states is the regular expression that describes the language of the DFA. And then you prove that that's equivalent. And this is basically the picture that you need to understand that. It's really not that hard. You have QI and QJ, and then you have this intermediary QRIP. And then there's 3 regular expressions. There's one from QI to QRIP, Q2 from QRIP to itself, and then R3 from QRIP to QJ. And all you have to do is take R1, R2 star, R3 union R4, and that describes RIP. This arrow describes exactly the same as these arrows. So this is how you recursively remove states from a GNFA. And so then, they give you a formal definition, blah, 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 blah. The inductive proof, that's fine. And then you work with some examples. This is, again, it's like I would definitely work through this example. We did it yesterday. Okay. This one was crazy. So this shows you just how big these regular expressions are. You get this simple, I would say, semi-simple 3-state NFA, and it ends up being this massive regular expression that describes that language. But still, it shows you that it works. Okay, now we're on to the new stuff. Okay, this is the new stuff. Non-regular languages. And this is probably the it's and it introduces an extremely powerful tool for understanding the power of regular languages and also showing that certain languages are not regular. And the way that happens is through this thing called the pumping. We'll get to the pumping limit, but I wanted to say, I wanted to read through this because there's some good stuff in here. Okay, to understand the power of finite automata, you must understand their limitations. In this section, we show how to prove that certain languages cannot be recognized by a finite automaton. So take 0 to the n, 1 to the n for n greater than or equal to 0. So, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, that kind of thing. If we attempt to find a DFA that recognizes it, we discover that the machine seems to need to remember how many zeros have been seen so far as it reads the input. Because the number of zeros isn't limited, n could be anything, the machine will have to keep track of an unlimited number of possibilities, and it can't do so with a finite number of states. So next we present a method for proving that languages like B are not regular. And it says, doesn't the argument already given prove, and this is, I really like this book because when I read that, I was like, yeah, that seems like proof. Because the number of zeros is unlimited, does not, just because the language appears to require an unbounded memory, doesn't mean that it's necessarily so. It does happen to be true for the language B, but other languages seem to require an unlimited number of possibilities, yet are actually regular. Okay, so this is really cool. C is the language of strings such that there's an equal number of zeros and ones. And D is the set of strings that have an equal number of 0, 1 and 1, 0 as substrings. So it turns out that C is non-regular, which kind of makes sense. And D is regular, which is pretty cool. And I think it's because like say you go from 0 to 1. Say you start with a 0 and 1. If you stay at 1, then you stay at 1. So, but if you go to a 0, then it has a 1, 0 substring, and you've canceled them out. So there's no way of generating 2 0 1s without generating a 1 0. Right? That's sort of the key to that thing. So pretty cool. All right, so let's get to the pumping lemma. So the pumping lemma is basically the way that I'll read the theorem, but the way that I like to think about it is just as unique. Okay, let's read it. So if A is a regular language, then there is some number P called the pumping length. Now, if you have some string in the language A, so we'll call the string S, that's at least P long, then S can be broken up into an X, a Y, and a Z portion so that their concatenation is equal to S that satisfy the following conditions. Okay? If you take Y, so for every I greater than or equal to 0, if you add copies of Y, then you're still in the language. And that's pumping it up. You pump it up, pump it up. You take Y and you pump it up. And so we require that Y is not the empty string, so it has to be something, because otherwise it would be trivially true for anything, right? If you could just always add the empty string and it just eliminates, it doesn't matter. Because anything concatenated with the empty string is just itself. It's like the identity element. And then the third condition is that the length of X and Y together is less than or equal to the pumping length. Okay, and this definition is honestly something that I have personally needed to work with through examples and just thinking about it for a while before it even started to click. And I don't fully, it's kind of hard to wrap your mind around. But basically, we'll just go to the picture. So, okay, so here's this picture. And basically, if you just think about a graph, the DFA is a graph. Let's take the pumping length to be the number of states of our DFA. Because we assume, so if A is regular, then it satisfies those properties. So since A is regular, we have a DFA. Now, what we do is we take that pumping length to be the length of the number of states. So if we have a string that is that length, then we're going to have that many number of hops. So we're going to have one more than the number of state number of hops. Now, the only way that that's possible via the pigeonhole principle is that we have some loop. There has to be some state that you've returned to twice. And basically, if you have some loop where you start and end at the same state in your DFA, then you could just keep taking that loop as many times as you want. And so that's what you're going to pump up. So that's the idea, right? Is it all relies on the pigeonhole principle. It's like, okay, we have this many number of states, but we're taking more hops than that. The only way that we could possibly take more hops than that is that there's a repeat. There's a loop. And so we pump up the loop. And we'll use this basically, and I want to, there's a detail in here. If S is any string in A. So to show that something's not regular, we just need to find one string that has no way of being pumped and staying in the language. Now, it could be that A is non-regular, and we still pick an S that can be pumped. So we just need to find one that can't be pumped. Pump it up, pump it up, pump it up, pump it up, that kind of thing. Is my mic working? Okay. So that's the proof idea. And there is some detail in here that's important. If no strings in A are at least length P, so I think that you can show that if the cardinality of the language A is infinite, is infinite, so let's say the cardinality of the naturals, because it's definitely not actually, I think the cardinality of the everything language. So let's say we have a 2-letter alphabet. We're almost always going to be working with a 2-letter alphabet. I think via Cantor diagonalization that actually the language that accepts all 2-letter bit strings is uncountable. Interestingly, though, I think that's actually kind of wild. I never thought about it like this, but if you have a 1-letter alphabet, then it's wow, that's kind of amazing. If you have a 1-letter alphabet, then it only has the cardinality of the naturals. But if you have a 2-letter alphabet, then the thing that accepts everything is a cardinality of the reals. So anyway, but let's just say it's infinite. I think you can show that if the language has an infinite number of strings, then there is going to be strings of infinite length. I don't think it's possible to have a set of infinite things and still have a bounded strings of bounded length. Is it possible to have a language that is infinite? Yeah, that have an infinite language that whose accepting strings are all bounded in length? I think obviously not. Okay, so anyways, what I'm trying to say though is that if there is no strings of the pumping length, I mean, yes, then all this stuff is true, but also I think you can say that any language with elements who are all have bounded length must be finite. So then, if all the strings in a language are bounded, have a upper length bound, the set must be finite because there's only a sigma cardinality of sigma to the bound possibilities. So sigma is the alphabet. Then you can just use the fact that we have a finite language to show regularity. Because the thing is, if you are guaranteed to only need a finite amount of memory, then you could just build a big DFA that does it. Yeah, right, exactly. This is what you do. This is what we went over yesterday that I need to remember. The proof that every finite language is regular. The proof that every finite language is regular is you just collect all the elements. So like you just collect every string in the language and you take the union of it. So it's the big U of W for W in L. Okay, easy. Easy, easy, easy. Okay, so we just went over some of the properties of the pumping lemma, and we went over, remember, you're basically just trying to find a loop. And so now what we're going to do is start to show specific languages that are not regular by basically, oh, and it's important to note that this is a necessary but not sufficient condition, meaning it could be that A is not regular and still satisfies this, but if it is regular, then it definitely satisfies this. And in here it says the pumping lemma give a necessary but not sufficient. So it's not sufficient to just show that these things hold and then be like, well, it's regular because, and then they give a construction here. I didn't read through this, but they give a construction that, look, here's a non-regular language that can be pumped. I'm sure that's a very interesting construction. All right, let's move on to an example of this though, because so this one's cool. Okay, I like this example because take 0 to the n, 1 to the n, like we had in the introduction. So the empty string is part of this, but also 0, 1, 0, 0, 1, 1, etc. So what they do is they take the pumping length, and we choose our s, because what we're trying to do is we're trying to show this is not regular. So we need to find a string in the language that cannot be pumped. And if we do that, then we know that the language is not regular. Because for a regular language, every string in the language can be pumped. You just need to choose the right y. Okay. So if P0 is followed by P1s. Now, the idea here is to find all the options for y and try to pump it up. So the first thing, let's just take y to be a single 0. If we pump that up, then these are not equal. The number of zeros and the number of ones are not equal. Okay, the second thing we do is we try to take the middle. So we got like 0, 0, 0, 0, 1. We take that middle, we take 0, 1. But if we pump that, then it gets, so take y to be 0, 1. If you pump that up, then you're going to get a 0, 1, 0, 1, which is not in the language, clearly, because it needs to be an equal run of zeros, followed by an equal run of ones. So that can't be pumped. Now we try 1. Okay, so y is just like a 1. And x and z are just the rest of it. Okay, so if we take our y to just be a 1, if we pump that up, again, it's the same as the 0. It's like, you can't do that because you're going to have an unequal number of zeros and ones. And then they give, and this is something that I had to work through for a while to understand this. So contradiction is unavailable, but also we can simplify this argument by removing 2 of our cases of the ones and the zeros just by applying condition 3. So condition 3 is interesting. It's that x and y are less than or equal to the pump length together. And basically, imagine a DFA that has P states. Then if our string, basically it's just saying that the loop has to occur in the first P characters. So the loop has to occur within the first P characters. And you just have to, and the thing is, it doesn't tell you what P is. In the pigeonhole proof, we just take P to be that state, but it just says that there exists a number P. And so the point that I'm trying to make, though, is that what he's saying here, we can simplify this argument, is that because let's say that P is still the number of states of this DFA that we've assumed to exist for contradiction, then, and it has P states or something like that, then Y must be made of only zeros, because the loop must occur in those first P states. So then you can just try to pump up the 0, show that that doesn't work, and then you don't even need to test the 1 or the 0 in one case. So that's really cool. This is another example. Equal number of zeros and ones. So they take the same string as before. So, oh yeah, so this is the interesting thing. So S is clearly part of the language, because this string will always have, no matter what P is, an equal number of zeros and ones. And its length is clearly more than the pump length. So we can rewrite S as 3 pieces. And then we can pump it up. We can pump Y up. We're trying to show that this is impossible, but it is possible. In this case, they let X and Z be the empty string and Y is just the whole thing. So we picked a bad case. But now this is where that condition 3 comes in again. Okay, here condition 3 in the pumping lemma is useful. It stipulates that when pumping S, it must be divided so that X and Y together are less than or equal to the pump length. That restriction on the way that S may be divided makes it easier to show that the string S is equal to 0p, 1p we selected cannot be pumped. So if xy less than or equal to the length of p, then y must consist of only zeros. Right? And therefore, if you pump it twice, it's gonna break the balance. Selecting the string S in the example required more care than example. If we had chosen, 0, 1 to the P instead, we would have run into trouble because that string cannot be pumped. Because we need a string that cannot be pumped, and that string can be pumped. Even taking condition 3 into account. Wait, can you see how to pump it? I thought you could just pump it. Oh, yeah. The reason why is because you can't just take it to be 0, 1. But I think you could also... Oh, yeah. Yeah, this works. Because X and Y together need to be less than or equal to the length of P. So you can't make this. You can't make Y. You can't just let Y equal this. So you let Z be the tail, but then you can still pump up the Y. If you fail in your first attempt to find a string, just try another one. Oh, and this is a way cleaner way to do these proofs, by the way, is once you have like a base of things that are non-regular, you just use the closure operations. the regular operations to show non-regularity. So an alternative method of proving that C, the language of equal number of zeros and ones, is non-regular follows from our knowledge that B, the one that we just showed, is non-regular. If C were regular, then C intersection 0 star 1 star would also be regular, because we can easily show that 0 star 1 star is regular, and the regular languages are closed under intersection. But the intersection of C and 0 star 1 star is B, and we know that B is non-regular. So that kind of like starts making our proofs a lot easier. This one's cool. WW, where W is anything. So we just need 2 copies. Okay, so this says that Y must be all zeros. But then you can't pump it. Because without it, we could pump S if we let X and Z be the empty string. Exactly. But with condition 3, the proof follows because Y must consist of only zeros. This is a very awkward. Anyways, they just show non-regular unary language, which is great. This one's cool. That sometimes, so remember in the definition of the pump, or in the statement of the pumping lemma, it requires that I be greater than or equal to 0. So you can actually pump down. You can remove the loop. And you can remove the loop, and that so we take 0 to be P plus 1 and 1 be, so this is the language. A run of zeros and a run of ones such that the zeros are bigger than the ones. Then we let our representative string be 0 to the P plus 1, and then 1 to the P. So Y must be a 0. If you remove the 0, then they're going to be equal, and then they're not in the language. So you can pump down. You can go downward. All right, it's time to get to the exercises. Let's go. I've been dying to do these exercises. I have been dying. We've just been talking and talking and talking. So let's hop in here. All right, let's do this thing. Okay, so the first exercise is, all right, I'll just draw these. So this is Q1, Q2, and Q3. We have a B. We have an A. We have an A. A, B. We have B. I think that's it. So this is M1. Okay, then the questions are, first off, what is the start state? The start state, Q1. B, what is the set of accept states? The set of accept states are going to be Q2, and that's it because we have the double circle here. Okay, C, What sequence of states does the machine go through on AABB? So we have AABB as our input. So here's what we're going to do. We're going to start at Q1, and we're going to follow our A arrow and go to Q2. Then we're going to go along A to Q3. Okay, then we're going to go to B, which is Q1. And then on B, we're going to go to Q1. Okay, so that's the set of states. Now on D, does it accept? No, it doesn't accept because it ends in Q1, and Q1 is not in our set of accept states. Okay, E, does the machine accept the empty string? No, because start Q1 is not an element of accept set. So, no. Okay, now our second one is, so let's draw this. This has 4 states. 1, 2, 3, 4. This is Q1, Q2, Q3, Q4. Can we see that? That's not bad. Okay, this is an accept state. This is an accept state. This is the start state. A, B, A, 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 B, B, B. I think that's everything. We can always check 2 out arrows. Because it's a DFA, we can just count the number of arrows. 2 out arrows, 2 out arrows, 2 out arrows. Okay, so this is a complete set. So now, what is the start state? Start Q1. B, the set of accept states is going to be 2 states. It's going to be Q1 and Q4. Okay, describe AABB. Okay, so we're going to get, so it's going to be Q1, then we take an A back to Q1, then we do another A to Q1, then we go to B, Q2, and then Q4. Okay, does it accept? Yes. E, does it accept the empty string? Yes. Q1 is in, so let's say this is F for the final, F for final, then we get that. So this DFA accepts AABB, and it accepts the empty string. All right, problem 2. Give formal descriptions of M1 and M2. Okay, so let's just look at the first one. What is it going to do? It accepts a run of B's followed by a single A. So if it ends in A, so okay, so look at this. So wait, actually, if you go A, it accepts. If you go A again, though, you don't accept. So what I think maybe happens is that if this let's see, if you go A, B, A, I think that this is, I think that so this is M1 and this is M2. So I think M1 accepts if there is an even or odd number of A, but I can't tell if that's too general. No, because that's not right. That's definitely not right. Because look at this. You go A, then you go B, then you go A. So that's not right. This is wrong. Try A, B, A. It definitely has something to do with ends in an A. I think it might just be that it ends in an A. I think it's M1 accepts if ends in A. Yeah, that seems right. Okay, so then B for M2, what does M2 do? M2 accepts the empty string. It also accepts any run of A's. But if you get a B, okay, so wait, so let's just state what it accepts. Any run of pure A. So that's in L. We're going to call L the language. So that's one thing. The second thing is if you start with a B, it also is going to accept any run of pure B with length greater than 1. So if you get a single B, it's going to deny. But if you get two B's in a row or greater, then it's going to accept. Now let's try A, B, A, B. What does this thing do, man? What does it not do? If you get a B, so if you get a B after run of A is not in the language. So if you go B and then A, you're gonna deny. This is like okay. You go B, then you go A, you go A, you go B. Okay, let's just try it. So B B A. Okay, it looks like another thing where you have to end in a B. unless you're only A's, you have to end in a B. So it might be any string that ends in a, so it's either a run of pure A's or anything ends in B. Maybe? Okay, so that's gonna be my answer. Okay, so we're gonna check these later, but I think it is. It's just you can do a run of A's, or you can do anything as long as you end in a B. No, but that's not true. That's definitely not true. Because if you end in this B, then you could just take a bunch of A's and you're still there. So that's not true. Because consider B A B A. B A B A. This is really hard because B A B A A B A. Dude, I don't know. I honestly don't know. I really don't know what this DFA is supposed to do. Okay, let's just move on. We'll check the answer to this. I'm pretty sure I got A correct, which is it accepts anything that ends in an A. Okay, so problem 1.3. Okay, so we're gonna get the DFA. Oh, this one's fun. I've done this one before. So M is equal to the tuple, let's say Q is equal to Q1 through Q5. So we have 5 states. We have 2 sigma. Sigma is equal to the set U, D. So those are our alphabets. Then we have our transition function. Then our start state is Q3. So this is start. Let's see, is this all in frame? Okay, the start. And actually, you know what I'm going to do? This. Closer. Okay, that's the start. And then the accept state is accept is the set Q3. So okay, and then delta, we're going to give delta here. So we have U, D. Okay, then we have Q1, Q2, Q3, Q4, and Q5. Okay, so basically remember, for a DFA, the type signature of the transition function is from Q with the product of sigma to Q. So that's the type of the function. Okay, so if you're at Q1 and you get a U, you go to Q1. If you're at Q1 and you get a D, you go to Q2. I mean, they give you this hint by calling them U and D. It's obviously up and down. So Q2 goes to Q1, Q2 down goes to 3. This is going to go to Q2, Q4, Q3, Q5, Q4, Q5. Okay, so let's draw our 5 states. Let's draw them like this. Okay, so this is 1, 2, 3, 4, and 5. All right, so if we're at 1 and we get a U, then if we get a D, we go down. If we get a U, all right, so that one was really easy. So that's the state diagram. So that was easy. That's the whole problem. Where am I? Okay. So 1.4, each of the following languages is the intersection of two simpler. So each L is equal to L1 intersect L2. In each part, construct DFAs for the simpler. So make DFAs for L1 and L2. Combine them using the construction Okay. I will be right back. So this first one seems pretty easy to get the L1 and the L2, but I'll show you how in a second. All right. I actually remember this one when I did it. This is really fun. Let me just write it down before I get in my head. No, whatever. So L is equal to W such that W has at least 3A and 2B. And at least 2B. Okay. All right. So the first thing we're going to do is L1 at least 3B or A. So what we're going to do is we're going to make let's do 4 states. So if we have an A, an A, an A, A, B. So this is going to accept anything that has at least 3 A's. So here we can just make this B, B, B. Oh, and then you have to make this accept and this the start. Okay, then L2 at least 2B is going to be the same construction. It's going to be 1, 2, 3, start, accept, B, B, A, 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 B. Okay, now it's time to do the Cartesian product. So now this is going to be L1 union L2. So, okay, so I remember the first time I did this problem, I did it really janky. But what you need to remember is that, so L is equal to the union. So the DFA for L is going to have Q equal to Q1 cross Q2. So this is going to be equal to, let's say this is like 1, 2, 3, 4, and we call this 5, 6, 7. Then we're going to have the states, 1, 5, 1, 6, 1, 7, and so on, 2, 5, 2, 6, 2, 7, 3, 5, 3, 6, 3, 7, 4, 5, 4, 6, 4, 7. So what I'm going to do is I'm going to draw 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This is going to be our start state, okay? So this is going to be A. This is going to be A. This is going to be A. But now, and let me actually, let's page 46. So see how this is an and, not an or? That's going to guide how we do the accept state. What do you say, 46? Okay, so that's going to be Q. F is going to be F1 intersect F2. All right, so what I'm looking for here is the delta. Okay, so let's just work out that. Okay, so let's just do delta of 1, 5. Okay, so this is going to be equal to, from the book, the pair delta. Oh wait. This is, say this is an A. So we're gonna get a delta 1, 1 A, delta 2, 5 A. Okay, so this pair is going to be equal to, so delta 1, we come up here, delta 1 on an A is going to be a 2. So this is going to be a 2, and then 5 A is going to be 5. So this is going to go to 2, 5. So that's going to be here. So I already drew that, but that just works out what it's going to be. Anyways, what you end up with is, so let's do, so this is going to be state, so this is like 1, 5. This is going to be like 4, 5. So let's just do delta of 4, 5 on a B. See where that goes. This is going to be equal to delta 1, 4 B, delta 2, 5 B. So delta 2B is going to be 6. Delta 1 is 4. So we're going to get 4, 6. This is 4, 6. So this is going to be a B. Anyways, what you notice is you get this like lattice. You get a B, and A's. And then at the bottoms here, we get B's. And then this is going to be the except state because it needs both. This is going to be a B. This is going to be an AB. B. A. Okay, I think that's it. So that is the answer to problem 1.4. Damn, that's only one of them. All right, we're not going to do all of these. Okay, let's do 1.4b though. 1.4b. All right, so this one is L is equal to W such that W has exactly 2 A's and at least 2 B's. Okay, so this is going to be L1 intersect L2. So L1 is equal to the set of strings such that W has exactly 2 A's. Okay, how are we going to do that? So what I'm going to say is we're going to have 1, 2, 3, 4. If we go A, we accept. If we have another A, you're dead because you can never remove A's. So and then the rest just have B's. B, 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 B. And then L2 is at least 2 B's. It's going to be the same thing as before. It's going to be like B, B, A, B, A. Okay, so again, we're going to have 12 states. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is going to be L. Bless you. Thank you. So so what I'm thinking is if we have, A, 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 B, 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 B. The accept state is going to be here. No, that's the skeleton. The idea here is, I mean, and then these are A, A, A. Basically, so remember the language is the set of strings such that there's exactly two A's. So here, if we have two A's and then any number of B's, and we can do anything, right? We go B A B A. We can go A B A B. We can do anything. We go B B A A A A B B. It doesn't matter. And then we can also go A A B B B B B B B. We can go. Wait. Yeah. So that's the answer. So for the language, exactly two A's and at least two B's. We use the intersection construction to with that Cartesian product on DFAs to take these two. So this is L1 is equal to and L2 is equal to, and then we just take their Cartesian product of their states. We take the intersection of their accept states. This is an accept state, and then we're good. All right. So the next problem. Let's see. What else do we want to do? Maybe we'll do the ones where we can check. Has an even number of A's, and each A is followed by at least one B. Okay, let's do this one. This one looks hard. This is the language L, where W such that W has even A's and each A followed by at least one B. This is going to be interesting because each A is followed by at least. So this one is easy. Even is easy. But this one, if each A is followed by at least one B, then the empty string should accept, right? All right, so let's just get started. All right, so for L1, it's just going to be this. So this is the language that accepts an even number of A's. L2, each A is so I think it's going to, so the first thing that I notice is that the empty string should work. And then I think that this is going to be B is here. We have another thing. This is going to be an A. I think that this is going to be a B. Each A is followed. So if you get two A's, if you get two A's, so then you should get an A here. You reject. So you can go B, 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 A, B, 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 A, B. But if you go A, A, then you get trapped in this third state. I think that that is true. But I'm trying to think. Okay, so now we just need to take the Cartesian product. So we're going to have 6 states. So let's draw 6 circles. 1, 2, 3, 4, 5, 6. So this is going to be L equal to L1 intersect L2. So the start state is going to be that. And it's also going to be because the intersection, because the final states or the accept states is equal to F1 intersect. Wait. What am I trying to say? It's going to be F1 cross F2, which is equal to, so if this is 1, 2, 3, 4, 5, then we're going to get just the set 1 cross the set 3 is equal to 1, 3. So this is 1, 3. All right, so I'm going to actually... Okay, so this is 1, 3. This is 2, 3. 1, 4, 1, 5. 2, 4. 2, 5. So delta of, let's say 1, 3, A is equal to delta 1, 1, A, and delta 2, 3, A. So delta 3A, this is going to be a 4, and this is going to be a 2. So we're going to get a 2, 4. So this is the A error. And then let's do 1, 3, B. This is going to be equal to 1, because a B is right there. And then I guess it's 3 there too. Okay, 2, 3, A. So 2 on an A goes to 1. And 3 on an A goes to 4. Um, 2, 3, B. 2 on a B goes to 2. 3 on a B goes to 3. Okay, 1, 4. 1 on an A goes to 2. 4 on an A goes to 5. So 1, 4, A. Right. 1 for B. So 1 on a B goes to 1. 4 on a B goes to 3. So right now, if you go B, okay, so we need to do 2, 4. So 2, 4, A. So 2 on an A goes to 1. 2 on an A goes to 1, and a 4 on an A goes to 5. 1, 5. Now 1, 5. 1, 5, A is equal to. So 1 on an A is 2, and 5 on an A is 5. So this just goes. And then 2, 5. Oh, wait, 1, 5, B. One on a B is 1. And 5 on a B is 5. So B is trapped there. And then the last one, 2, 5. 2 on an A goes to a 1. Do we have everything? There's 2 out arrows, 2 out arrows, 2 out arrows, 1 out arrow. 2, 4. 2, 4, B. So 2, 4 on B is a 2 on a B goes to 2. A 4 on a B goes to 3. A 4B goes to 3. So this is going to go to 2, 3. So this is a B. Let's make sure that we should have 12 arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this is complete. Let's see if it does what we want. So if we go AA, if we go AA, we're trapped. No matter what we do, we're trapped in here, I think. If we go A, B, A, B. Okay, cool. A, B, A, B. A, B, A, B. All right, I think we're good on that one. So this is 1.4D. Let's check. Well, we'll check after. We'll check our answers after. I'm pretty sure that's right. Okay, let's see. Did we do everything? So we constructed DFA for the simpler language and combined them using the Cartesian product construction. All right, so we did three out of this. That's pretty good. And we did the. All right, you know what I'll do? I will actually check the answers. All right, so for 1.1, I got Q1, the set Q2, Q1, Q2, Q3, Q1, Q1. Yep, no and no. Perfect. So this is correct. Then Q1, Q1, Q4, Q1, 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 Q2, Q4. Okay. And then yes and yes. Nice. Oh, they wanted you to. Oh, okay. I didn't do 1.2 correctly. Yeah, okay. I thought they were trying to have you qualitatively describe what it is, but not. Okay, that's fine. Okay, 1.4b. That's exactly what I got. Hell yeah. They say you can simplify it. I don't really care about that. Okay, let's see if we got this right. Nice. And then B A B B. Okay, cool. And then the construction here. Nice. All right, we did it. I didn't simplify it. I just did this. All right. Time to move on. 1.5. In each of the following languages, is the complement of a simpler language. Construct a DFA for the simpler language. Then use it to give the state diagram for the language given. Okay. All right. So L is equal to the set W, such that W, I'll just say that AB is not contained in the string. That's how I'll write it. Okay. So we need to convert this to a DFA. Actually, can you do it with 2? You go A, B. No. You can't do that because you have to. You need this one because you can't. You can't do. So yes, you go B B B B B A A A A A A. Then B is an accept. So then I'm pretty sure so this is L complement. So then L should be equal to and then this A, B. I'm pretty sure it's that. So you just flip the accept states and the non-accept states. Okay, I'm gonna get some water. Okay. So what's next? What are we doing? So I think we did that one, right? All right. We're not going to do too many more of these. But we're going to do B. I want to do all of the ones that have answers cuz then we can double check. But I think that this one's going to be the exact same. Doesn't contain Baba. So if you do contain Baba, you're going to go B, A, B. Wait. So if you get an A, or I think what we can do is we can actually do. No. You have to go. So then, if you get an A here, you need to go back to this guy. So if you go B, A, if you go B, A, A, B, A, B, A. So if you go. If you go to B here, you have to go back to the start. I think that's correct. Okay, so we're trying to construct the deterministic finite automaton that doesn't contain Baba. So first, we're making the language L complement is it's going to accept any string that contains Baba. You go A, B, A, B, A, B, B, A, B, A, and then you can do whatever you want after that. You can also go B, B, A, B, A. But then if you go B, A, A, then you need to go back to the start. So I'm pretty sure that's correct. Let's look at the answer for 1.5a and 1.5b. 1.5a. Let's see, we got B, A, B, A, B, and then you just flip the states around. And then this one is okay. So what I did. Oh, I guess. Okay, I guess on the B, this is supposed to go to here. Right. Yeah, that needs to go to there. Okay, so this arrow I got wrong. Because this B counts as the first B in Baba. So otherwise you would require from that branch a BB ABA. Okay. Okay, 1.6 give state diagrams. Let's just read through some of these maybe. W says that W begins with a 1 and ends with a 0. All right. Let's just get on with it, right? 1.6a. Give state diagram for DFA. All right. So A is W says that W starts with 1. And, I'm going to call it A and ends with B. Okay, so let's just start with this thing. This is the start state. If you get a B at the beginning, then you reject. I mean, this is you can just A B this, because if you start with a B, then you're just never going to accept it because the first thing is wrong. But now if you get this first A, you got the first thing down. And then you should be able to just go like this, A. And if you get a B, this is the accept state. And B goes back to itself. But then if you get an A here, you can go to here. Okay. So what's next here is I think that's just it. I think that's it. So if we get an A, then we should be able to do whatever we want. B, A, B, A. As long as it ends with a B, it's good. And if you start with a B, then you're forever in hell. Okay, let's see what's next. B contains at least 3 ones. All right, we can just talk about some of these because we don't really need to draw the whole thing out. Although it does lead to a lot of issues. Okay, if it contains at least 3 ones. Okay, we can just do that really quickly. Okay, so you start out with a B. If you get an A, then you go to the A count. This is like the A count equals 1 section. And then you get another A. You got, sorry, okay, I got 2 A's. And you go to, I got 3 A's. All right. And then this can just be A, B. B, B. We've done so many of these. These are so easy at this point. Okay. I think that one's right. Okay. C. C contains the substring 0101. I like these. These are fun, actually. What I'm thinking, so I was gonna do this one, but this is literally the exact same as the complement of the Baba one. So it's like we just did that one. We don't really need to do that one. D seems easy though. Well, I'll do D just for fun. W such that length of W is greater than or equal to 3 and W index number 3 is equal to an A. Okay, so that one is pretty easy. So we're one indexing here, just FYI. Okay, so this is going to be A, B, A, B, A, B, oh wait, B, A, B, A, B. So this should make sense, right? So first two can be anything, but if the third is a B, you go to this reject state. If the third is an A, you accept and you can do anything you want after that. Starts with 0, has odd length, or starts with 1 and has even length. That one seems kind of fun, right? Okay, so let's just knock out some of the ones that we can just talk about as the answer because it's really like obvious. So doesn't contain the substring 110. You do the same thing as the Baba one. Basically, you make the thing that accepts only if it contains 110, and then you just complement the accept states. So the new accept states will be the complement of the old. This one is easy. You basically just have what is it going to be? 6 states. It's going to be 7 states, I think. The first 6 are going to be whatever you want. Then if you get anything after that, you reject and you stay there forever. Um, that one might be fun. Because if you get a 110, then you go back. If you get a 1-1, you reject. Maybe H. Okay, so which ones do I want to do? I want to do E, H. Let's see. I. Every odd position is a 1. How are you gonna do that one? Okay, I should be easy, but I want to do I. Because what you're gonna do is you're just gonna, let's say you're at your start state. Let's say you get an let's say you, so in our case, let's say you get a 1. Then you're good. Then the out arrows are anything, 0 or 1, back to your start. But if you get, okay, I'll draw it out. That one's fun and easy. J W contains at least 2 zeros and at most 1. This one's the same as the Cartesian product ones we did already. Ooh, K is good. I want to do K. Maybe L would be good because the thing that we did in 1.4 was the intersection, but we want to do a union one maybe with an or. The empty set, I'll show you guys this one, but it's in the book. It's like pretty in the book. Oh, yo, I didn't see your comment, dude. What's going on? All right, so let's just get started. We're gonna do E right now. So let me switch over. All right, so I'll write it out. So E is, so this is 1.6 E. Let's see, are we in frame? Okay. This is the language where W, such that W starts with an A and has odd length. So that's like one clause. Or starts with a 1, starts with a B, and even length. All right, so we're gonna use our, so we're gonna make this as L is equal to L1 union L2. So it's gonna be our union construction, where so first we're gonna make L1. So so we go here. If we get a B, oops, I always do that. If we get a B, then we're in this reject state, and we're never gonna get out of there. But if we get an A, then we're in an accept state. But if we go here with an A or a B, oh wait, I don't think that we're gonna do this. I think we're gonna go like this: A, B. Okay, so see what's happening here. So if we don't start with an A, and we start with a B, we would just reject completely, unequivocally, and we can't get out of there because both letters send it to itself. So we start with an A and we're good. We can accept just the string A because A is odd length. But if we get anything else, we're now at an even length and in a reject state. But if we do anything else, we go back to odd, and thus we accept. So this is L1. L2, on the other hand, we're still going to have this 1, 2, 3, 4 thing. But here we're going to have a B, an A, an AB, Now this is also going to be AB except AB. Okay, I think that's everything. That's cool, bro. All right. So, oh, and this is our start state. So if we start with a B and we have even length, so now what we have to do is we need to take the union of these. So we're actually going to have 16 states. This is going to be a pain in the butt to do. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So we're going to number these 1, 2, 3, 4, 5, 6, 7, 8. So these are gonna. This is the state of the Cartesian product construction. So this is going to be like 1, 5, 2, 5, 3, 5, and 4, 5. This is going to be 1, 6, 2, 6, 3, 6, 4, 6. 1, 7, 1, 8, 1, 9. Oh, wait. What am I doing? 1, 7, 2, 7, 3, 7, and 4, 7. 1, 8, 2, 8, 3, 8, 4, 8. Okay, so these are all of the states of our DFA. Now, let's just go through it, man. So we got this. We got 1, 5. So we're trying to compute delta of 1, 5 with an A. This is going to be equal to delta of 1A. So that's 2. Delta of 5A is 8. So we're going to go 2. So we're going to go 1, 5 to 2, 8 here. Oh, and we want to figure out the accept states. So I'm pretty sure. Okay, so let's just look at the textbook really quickly. So in the Cartesian product construction, F is going to be equal to R1, R2 such that R1 is in F1 or R2 is in F2. Well, there's this crazy ant on my screen. It's a big ant. Okay. All right. Continuing on. So that means that as long as we contain one of the accept states. So let me switch back over here. So the accept states, so F is going to be equal to to anything and anything 7. So like these are all going to be accepts, and these are going to be all accepts. Okay, so we go to 2, 8. Now 1, 5B, 4, 6. This is going to be a total mess. 2, A, 5A, 2, 5, 2, 3, 8 on an A. This is going to be 2, 5B now. 2, 5 on a B. To 2 on B is going to go to 3. 5 on B goes to 6. This is going to be 3, 6. This is going to take a while. Okay, 3, 5A, 3, 5B, 4, 5A, 4, 4, 5B. Okay. So 3 on an A goes to 2. 5 on an A goes to an 8. Okay. 3, 5 on B. 3 on B goes to 2. 5 on B goes to 6. This would be a good one to revisit and look at the minimal, the optimized DFA. So this is a B. This is an A. This is going to be a total mess. Okay, and we're going to proceed like this. I think that we get the idea. I mean, as long as we got these down and I think that these are good, then we don't really need to do the whole thing. It's just going to take forever, and it's not going to be like that much more learning, really. But which ones did I want to do? E, H, I, K. E, H, I, K. So we did some of E. Now we want to do H. Any string except 1, 1, and 1, 1, 1. That's kind of a weird one. Any string except those. because it's not a contains, right? It's like it's not a contain operation. It's just exactly that. So if we have, so let's just say we have like a 1 and then a 1. Or let's say A, or let's say this is BB and BBB. So this is a B, A. Or wait. Hold on. Yeah, so if you go B, B, if you get an A, you can do whatever you want now because you've broken out of this thing. You know that there's no way that you're going to possibly, because it's not a contains. It's exactly BB and it's exactly BBB. So if it's this, you reject, and then also you reject this. But if you get an A here, and you could probably collapse these down, right? You could probably collapse this into there. Similarly here, also has an A. All right, I think that's it. So you're going to have, if you get a B, B, so here you accept, here you accept, these two you don't accept, and you accept this. Cool. Okay, H, now we want I and K. Okay, so every odd position. So we start here. If we get an A, then we have failed. If we get a B, we're good. But if we, and then we can come back here. I think that's it. Okay, what's K? K is L is equal to the finite set epsilon and A. Okay. So I think what we want to do is we want to start off. This is just epsilon. So we accept the empty string. Then if we get an A, we accept. But if we get a B here or anything else here, we reject with no chance of leaving. So empty string accepts. If you get a B, you reject. If you get an A, you accept. If you get anything after that, you go into your death state. Okay, cool. We're done with 1.6. Okay, 1.7. Let's start reading through this. All right, section or question 1.7 says give state diagrams of NFAs. So we've been practicing with DFAs a lot. Let's do NFAs now. with the specified number of states recognizing each of the following languages. In all parts, the alphabet is 0, 1. I convert this to AB because then we can number the states. I just prefer AB. I don't really like 0, 1. The language W that ends in 0, 0 or AA. Take a. Now that we did that problem, I'm going to take a 3-minute break. Okay. Ends in 0, 0. All right. I'm going to want to check my answer on this one. I think it might just be this. Nah, but this doesn't seem right. I think we need a B here. Because then you could do like BA. Oh. See, this is the DFA though. We just made the DFA for this thing. But we want the NFA. Okay, let's look at the answer. I don't know what it's supposed to be. Oh. Yeah. Okay. So the reason why I did this wrong is you need to remember that you can have 0 or more. In a sense, you have to be more clever to design NFAs because you can have all right, I'm gonna make some food, dude. The freaking leaf blowers. It's just all day, every day. You know what? And personally, I love it. I think we should have leaf blowers. I think for every square block, there should always be at least one leaf blower going constantly. It just gives the neighborhood that kind of nice, calming feel. You know, it's nice. And I love the like Sisyphean feeling of like we're all just moving leaves from one side to the other side. You know, move it to their yard, and then they move it to your yard, and it just goes back and forth. And what else is there but leaves blowing in the wind from a leaf blower? A nice, relaxing leaf blower. There's nothing better. All right, I'm gonna make some food because I can't stand this. I'll make it a pasta. I'll make a pasta. All right. So wait, I don't want to cheat on F. All right, we need to. Okay, so I do need practice with NFAs. So we're gonna do like a lot of these. Mm. Because the thing about NFAs is all you need is a single path. So you need to sort of shift your mentality. Mm. So B, hmm, 1.6 L contains an even number of zeros. Hmm. NFAs are really cool. NFAs are really cool. It really simplifies what you need to write down. How do you do that? How do you do F with one state with three states? I think I got it. Okay, so we're gonna work through B, C. We're gonna work through all of them. Once I'm done eating, we'll work through all of them. Mm. All right, let's hop into it. Okay, so we're doing 1.7. Give NFA with correct number of states. Sigma is equal to 0, 1. All right, so A, it's L is equal to the set of strings where W ends in 0, 0. Q of L is equal to 3. I don't know if this is NQ of L. I don't know how I would write that. It's really not of the language, it's of the NFA. So anyways, the 3 states. That's what we need to say. Okay. Okay, so here's what we're going to do. We just need a single path that ends in 3 states. So what we're going to do, first off, we're going to draw 3 circles. Then we're going to say 0, 1, 0, 0, and this is an accept state. So basically, you can plug around, you can chill out over here doing whatever you want. But you can non-deterministically, because you might not know when to, like, let's say we have like 0, 1, 0, 0. Okay, what we could do is go 0, 1, 0, 0. But then we're stuck. But the thing is, we go 0, we branch, right? So we're going to like, all right, so we're going to put like a 0 here. So this is called 1, 2, 3. So we start off at 1. Okay, then we get this 0. So this is our alphabet. So now we can either go to 1 or we could go to 2. But now we get a 1. and this dies because there's nowhere to go. But then 1, or let's call them A, B, and C. So then A on a 1 can go to A. Then it gets a 0. So now it can go to B, or it can go to A. So then here we can this is going to branch out too. So this can go to A or B, and this can go to C on this, wait, on this next 0. But then these are not accept, but this is accept. So 0, 0, 1, 0, 0 is in L. All right, so that's like the tree of computation look at that thing. So this is the NFA. All right, let's do B. Okay, B is language 1.6C. 1.6C is 5 states, contains 0101 as substring. Okay, so we're going to just start off with 1, 2, 3, 4, 5. Now here's what we're going to do. 0, 1. So it can take anything here. But we're also going to say 0, 1, 0, 1. And then here, 0, 1. Because this is the thing. We can branch non-deterministically. So this is really the superpower of NFAs, is like they're all going to die in these intermediates, but like, yeah. Anyway, so that's what it is. That's the answer. All right, let's do C. Oh, wait, that was right. Okay, 1.6L. This is going to be it's the language with even zeros, even number of zeros, or exactly 2 ones. How many states do we need? 6 states. I'm going to clean up really quick. Okay. Ooh. Six states? This one's hard, man. Even number of zeros or exactly two ones. Okay, so if there's any path that's like this, so this is like L2. Hey. Okay, we'll finish this up later.